Good morning, students. In lecture first of N.M.R, we discuss about the electromagnetic radiations, and the lecture number second we discuss the principle of N.M.R. Today, in lecture third, we discuss the width of absorption lines in N.M.R from MSc Final Chemistry, paper 5th, unit 2nd. The width of absorption lines in NMR. The separation of two absorption lines depends on how close they are to each other and the absorption line's width. The width of the absorption lines is affected by a number of factors, only some of which we can control. These are factors is first one is homogeneous field, second relaxation time, third magic angle NMR, and the fourth one is other source of line broadening. First point we discuss the homogeneous field. The most important factor controlling the absorption lines width is the applied magnetic field H0. It is very important that this field be constant over all parts of the sample, which may be 1 to 2 inch long. If it is not, H0 is different parts of the sample and therefore V, which is known as the frequency of absorbed radiation, will vary in different parts of the sample. These variations result in a wide absorption lines. For qualitative or quantitative analysis, a wide absorption lines is very undesirable since we may get overlap between neighboring packs. Second point is relaxation time. The relaxation time, the pulse has been removed, the spin system relaxes back to the equilibrium in two separate processes, which is called the relaxation. Means the second important feature that influence the absorption lines width is the length of the time that an excited nucleus stays in the excited state. Delta E delta T is equal to constant, where the delta T is the concentration in the value of E. Delta T is the length of time a nucleus spends in the excited state. Since delta E and delta T is constant when delta T is small and delta T is large, but we know that E is equal to h nu and that h is constant. Therefore, any variation in E will result in a variation of nu. If E is not an exact number but varies over the range E plus del E, then V will not be exact but vary over the corresponding range V plus del V. Then we have E plus del E is equal to H V plus del V. In one process, the Boltzmann population excess is restored due to nuclei relaxation from the beta spin state to the alpha spin state. We can summarize the relationship by saying that when delta T is small, delta T is large and therefore delta V is large. If V del V is large, then the frequency range over which absorption takes place is wide and a wide absorption lines results. In other words, the magnetization along the z direction grows from 0 and become equal to the original equilibrium value m0. This is called the spin lattice relaxation. The second process involves decay of mxy to 0 magnitude. This is called the spin-spin relaxation. When these two processes are complete, we once again have mx is equal to 0 and bulk magnetization m equal to m0 magnitude. The N.M.R repeats the process to get FIDs. Successive FID are added by the computer to cancel out the noise, thereby increasing the S upon N ratio to give us the spectrum. There are two principal modes of relaxation. First one, longitudinal relaxation, which is known as spin lattice relaxation, and the second one is transverse relaxation, which is known as spin relaxation. So we are early mentioned the removal of pulse. We need to wait till the system has returned to its original position. This process is called the relaxation, and this relaxation process is divided into two parts. First one is longitudinal relaxation, which is also known as spin lattice relaxation. When the nucleus loses its excitation energy to the surrounding molecules, the system becomes warm as the energy is changed to heat. This process is quite fast when the molecules are able to move quickly. This is the state of affairs in liquids. The excitation energy becomes dispersed throughout the whole system of molecules in which the sample finds itself. No radiation energy appears, no other nuclei become excited instantly. A numerous nuclei lose their energy in the fashion. The temperature of the sample goes up. This process is called longitudinal relaxation. The symbol we choose T1 means it involves the transfer of energy from the nucleus in its higher energy state to the molecular lattice. The energy is transferred to the components of the lattice as the additional transitional, vibrational, and rotational energy. The total energy of the system remains the same. An efficient relaxation process involves a short time and results in the broadening of absorption peaks. Smaller the time of the excited states, greater is the line width. This mechanism is not effective in solid. This process keeps the excess of nuclei in the lower energy state, which is necessary condition for nuclear magnetic resonance phenomena. The second is transverse relaxation, which is known as spin-spin relaxation. An excited nucleus may transfer its energy to an unexcited nucleus of a similar molecules that is nearby. In this process, the nearby unexcited nucleus becomes excited. Uh, the previously excited nucleus becomes unexcited. There is no net change in energy of the system, but the length of the time that one nucleus stays excited is shortened. This process is called transverse relaxation, which is denoted by T2. Means it is due to the mutual exchange of spins by two processing nuclei which are in close proximity to each other. We know that each processing nucleus is associated with the magnetic vector component rotating in a plane perpendicular to the field. If this small rotating magnetic field is the same as is required to induce a transition in the neighboring proton, then mutual exchange of spin take place. Now we can say in other words that it involves the transfer of energy from one nucleus to the other. There is no net loss of energy. The spread of energy among the nuclei concerned result in line broadening, which makes NMR spectra of solid comparatively more interesting, which is known as spin-spin relaxation. The third one is magic angle NMR, a problem with the examination of solid that are nuclei can be frozen in space and cannot freely line up in magnetic field. The NMR signals generated are depend among other things on the orientation of the nuclei. The randomly oriented nuclei therefore give broad band spectra which are not very useful analytically. It can be shown that when one rotates a solid sample such that its axis of rotation 54.7 degree to the direction of the applied magnetic field. The broadening caused by random nuclei orientation tends to be averaged out, resulting in narrower spectra. This is more useful analytically because it allows better resolution and therefore better measurement of chemical shift and spin-spin splitting. In turns, this is very informative of the functioning group and their position relatively to each other in the sample molecules. We can summarize the relationship by saying that when delta T is small, delta T is large and therefore delta V is large. If del V is large, then the frequency range over which absorption takes place is wide and a wide absorption lines results. In other words, the magnetization along the z direction grows from 0 and become equal to the original equilibrium value m0. This is called the spin lattice relaxation. The second process involves decay of mxy to 0 magnitude. This is called the spin-spin relaxation. When these two processes are complete, we once again have mx is equal to 0 and bulk magnetization m equal to m0 magnitude. The N.M.R repeats the process to get FIDs. Successive FID are added by the computer to cancel out the noise, thereby increasing the S upon N ratio to give us the spectrum. There are two principal modes of relaxation. First one, longitudinal relaxation, which is known as spin lattice relaxation, and the second one is transverse relaxation, which is known as spin-spin relaxation. So, we had earlier mentioned the removal of pulse. We need to wait till the system has returned to its original position. This process is called the relaxation, and this relaxation process is divided into two parts. This is very important point is gyroscopic precession. Means the magnets when brought together will align exactly parallel to each other and will maintain this alignment in static fashion. Magnetic nuclei, due to restriction described by quantum mechanics, do not align exactly parallel to or against the external magnetic field, but rather they align at an angle. This is an important consequence that can be illustrated by considering a gyroscope, which is shown in diagram, which is gravity pulling straight down. A gyroscopic place vertically will maintain this orientation motionlessly. If a force is applied to the gyroscopic perpendicular to the gravity field, it will rotate above an axis parallel to the gravity field, which is shown in this video. Means it will rotate about an axis parallel to the gravity field, demonstrating something we'll call precession. The frequency of this precession depends on two factors: the force extracted by the gravity field and the force exerted by the gyroscopic motion, which is shown in this video. Spin state population inversion. Magnetic nuclei such as hydrogen atom, when placed in a static external magnetic field, will always have a slight excess of population of atoms in the lower energy alpha state. By irradiating the nucleus with electromagnetic radiations, the correct energy, which is known as determined by its frequency, a nucleus with a low energy alpha orientation can be induced to jump to a higher energy beta orientation. The absorption of energy during this transition forms the basis of the NMR method and shows the diagram. The low energy level is alpha spin state and higher energy level nucleus is beta spin states. Radiation frequency versus the field strength. Strong magnetic fields are necessary for NMR spectroscopy. The international unit for magnetic flux is the Tesla, which is denoted by T. The Earth magnetic field is approximately 10-4 Tesla at ground level. For NMR purpose, this small energy difference delta E is usually given as a frequency in units of megahertz 10 to the power 6 hertz, ranging from 20 to 900 megahertz depending on the external magnetic field. The irradiation of a sample with radio frequency, which is denoted by RF energy corresponding to exactly to the spin state separation of a specific set of nuclei, will cause excitation of these nuclei in +1/2 state to the higher -I half spin state. यानी इसकी फ्रीक्वेंसी जो है जैसे 60 डायग्राम में शो है 60, फिर 100, फिर 200, 300 और 400, तो इनकी एनर्जी लेवल का जो डिफरेंस बिटवीन द अल्फा एंड बीटा स्पिन स्टेट, द वैल्यू ऑफ डेल्टा ई इज आल्सो इंक्रीज. द एनर्जी ऑफ ए फोटोन इज इक्वल टू h nu. Spin state energy difference, that is delta E is equal to gamma h b0 upon 2 pi when E is equal to delta E. Delta E is the energy difference between the alpha and beta. Spin flips occurs h nu is equal to gamma h b0 upon 2 pi. The necessary frequency is needed is equal to nu is equal to gamma b0 upon 2 pi. At 60 megahertz, we can say 1.41 Tesla, 100 megahertz 2.34 Tesla, 200 megahertz 4.73, 300 megahertz 7.07 Tesla, and the last one 400 megahertz, which is known as 9.56 Tesla. This is the proton spin energy difference between the alpha and beta, which is denoted by delta E. The width of absorption lines in NMR. The separation of two absorption lines depends on how close they are to each other and the absorption line's width. The width of the absorption lines is affected by a number of factors, only some of which we can control. These are factors. First one is homogeneous field, second